For this circuit, we want to find the current out of the source as t goes to infinity. The input's a sinusoid with a frequency of 6t. That means that we're looking for the particular solution. We'll get a sinusoid out for I of t, which also has a frequency of 6t. It makes sense to do this circuit in the frequency domain, so we can transform all the circuit components to their equivalent impedances. This inductor with a 1/3 Henry inductance is going to have an impedance of J times omega times 1/3, which is J2 ohms. This capacitor's impedance will be negative J over omega C, so that's minus J over 6 times 1 over 12, which is minus J2 ohms. And finally, this inductor's impedance is going to be J times 6 times 1 over 6, which is just J1 ohm. Now let's redraw the circuit in the impedance domain and go on with our analysis. Transformed all of our circuit elements to impedances. The resistor's impedance is, of course, just its resistance. Converted our voltages and currents to phasors. Now we just need to solve for I. This circuit looks like it's a natural for circuit reduction. These two circuit elements are in series. If I combine those will be in parallel with this impedance, and then that total result will be in series with the 4 ohm resistor. Once we've gotten that equivalent impedance across these terminals, I, as a phasor, is just going to be the voltage at an angle of minus 25 degrees over ZEQ. Okay, let's find ZEQ. As I mentioned, these two are in series, so their equivalent impedance is minus J2 plus J ohms, which is just minus J1 ohm. Then that impedance will be in parallel with this one, so on this side of the circuit, its impedance is J2 times negative J1 over the sum of the two, J2 minus J1. J times negative J is just 1, so this becomes 2 over J. Moving the J into the numerator becomes minus J2 ohms. Finally, ZEQ is just this impedance in series with the 4 ohm resistance, so it's 4 minus J2 ohms. And now, according to our original plan, the current phasor, I, is going to be 2 at an angle of minus 25 degrees over ZEQ, which is 4 minus J2 ohms. And if I convert the denominator into polar form, divide the magnitudes and subtract the phase, I'll end up with 1 over square root of 5 at an angle of 1.6 degrees. So converting that back into the time domain, I of t as t goes to infinity is going to be a sinusoid with a magnitude of 1 over square root of 5. Cosine of our original frequency was 6 radians per second, plus the phase is 1.6 degrees. And there's our answer. Now, as with any other circuit, there's not just one way to analyze it, so let's take a look at this circuit and analyze it using nodal analysis. Okay, it's still my frequency domain circuit. All of my elements are represented by impedances. My voltages and currents are represented by phasors. So I need a reference terminal. I'll call this node 0 volts. So this is going to be, I'm going to say this is V sub A. It's going to be a phasor. This is V sub B, also a phasor. Also, this is a dependent node. Its voltage is 2 at an angle of minus 25 degrees above 0, so that's easy to label. Now we just do KCL at our independent nodes. So KCL at A, VA as a phasor, minus 2 at an angle of minus 25 degrees over 4 ohms, plus the current through this element is going to be VA minus 0 over J2 ohms, plus the current through the capacitor is going to be VA minus VB over negative J2 ohms. KCL at B, the current through that capacitor is going to be VB minus VA over minus J2 ohms, plus the current through this inductor is going to be VB minus 0 over J1 ohm. That sums to 0, and I left off my summation to 0 here. Now, to be perfectly honest, at this stage, this algebra looks like it's going to turn out to be kind of messy, and I'd start looking for a different approach. But since this is just intended to illustrate that the approach is more or less arbitrary, I'll go ahead and slog through it. It looks like what I'm going to want to do is solve for V sub A, then I can find the current phasor I as this voltage minus V sub A over 4 ohms. So let's solve this equation for V sub B. If I multiply this through by minus J2 ohms, I get V sub B as a phasor minus V sub A plus negative J2 over J1 is just negative 2 is equal to 0. Do that. So V sub B is equal to negative V sub A. Now I can plug that in here and solve for V sub A. So this equation becomes V sub A minus 2 at an angle of minus 25 degrees over 4 plus V sub A over J2 plus V sub A minus V sub B, with V sub B meaning negative V sub A, turns out to be 2 V sub A over minus J2, and I forgot my phasor notation there, is equal to 0. So multiplying this through by 4, V sub A minus 2 at an angle of minus 25 degrees plus, let's see, 4 times this over 2 would be 2 V sub A over J. Multiplying this through, that cancels with that. That becomes a 4 V sub A over minus J is equal to 0. Moving this J into the numerator makes it a negative J, so minus J2 V sub A. This moved into the numerator becomes a negative of negative J, so that's plus J4 V sub A is equal to 0. So grouping the V sub A's, V sub A times 1 minus J2 plus J4, and then moving that over to the right-hand side is equal to 2 at an angle of minus 25 degrees. So V sub A is equal to 2 at an angle of minus 25 degrees over 1 plus J2. Now I'm going to make a little bit more room to work over here. I don't need these equations anymore. So now, as I said before, the current phasor I is the voltage 2 at an angle of minus 25 degrees minus V sub A over 4 ohms, which becomes 2 at an angle of minus 25 degrees minus V sub A, which is 2 at an angle of minus 25 degrees over 1 plus J2 over 4 ohms. I can factor out this 2 at an angle of minus 25 degrees times, let's see, this becomes multiplied by 1, so this is 1 plus J2 over 1 plus J2 minus 1 over 1 plus J2 all over 4 ohms, which is 2 at an angle of minus 25 degrees times 1 plus J2 minus 1 just becomes J2 over 1 plus J2 times 4. Simplifying that down is 2 at an angle of minus 25 degrees over, that cancels with that, becomes a 2. So this becomes J over 2 plus J4. If I multiply top and bottom by minus J, I is equal to 2 at an angle of minus 25 degrees times J times minus J is 1, minus J times J4 is 4, minus J2, which is the same answer we got for the current phasor before, and that will lead to the same answer for the current I of t. I guess the moral of this is that if you can do circuit reduction, that's probably going to be the easiest approach. There are exceptions to the rule, but I'll usually try to do circuit reduction first.